All right, thank you. Like you said, my name is Tim Mueller. I'm a graduate student at the University of Florida. And today I'm going to be talking about the evaluation of rail shear at concrete tub crossings. And we're going to go through a bit of a case study on this. Also notably on the project is Stephanie Bauman, Dr. Christopher Ferraro, and Dr. Kyle Riding. So today we're going to be talking about concrete tub crossings. And I'll give you a quick couple pictures here to get these in your mind. Concrete tub crossings are a type of railroad at-grade crossing that have seen use over time and have seen some increased use recently. And they facilitate the intersection of train traffic with vehicle traffic. So to give you a bit of the project background on this, these have seen good use. They have shown to provide good stability, provide little settlement with age, and show little need for maintenance. However, there have been some mixed opinions in the industry about these and have been some mixed concerns regarding these. And this came out of the fact that locally at the areas of these concrete tubs, you're going to have a higher stiffness than the areas of your typical track structure. So you're going to have a train now passing from an area of lower stiffness onto a stiffer surface and then back off. And this brought up fears about rail shear at these transition areas and possible safety concerns with that in terms of the trains, as well as damage to the structure itself. So the industry has now taken predominantly the approach of limiting speed through that because it's the fear at greater speeds, this becomes more of an issue and it decreased some of their own risk by traveling through at lower speeds. However, a lot of the stakeholders obviously would like to see an increase in this speed. The railroad industry would like to not have to slow down at these kind of crossings, maintain their speed. It clears up vehicle traffic quicker and whatnot. So this project was brought to us to see if we could make a recommendation on if this speed could be increased in a manner that was safe and did not have any negative effects to the structure itself. So here's back at these pictures, two pictures of concrete tub crossings, one at a plant where they're being made, and then one in place after several years of use. Notably, as you'll see in the picture of the left, we're going to be talking some about the restraint structure, those steel elements that hold the rail into the tub itself, and that's going to be important. So we were able to go to a number of these concrete tub crossings across the state of Florida, all of which were considered to be performing satisfactorily to the railroad industry. Almost all of them did not need any maintenance at all since they were put in place and showed what we know to be true of providing good stability and little settlement. But important for this case study was to find a location where we could have higher speeds going through that. And this brings us to Laramie, Wyoming. So in Laramie, Wyoming, we identified a concrete tub crossing in which there was no speed restriction for the crossing itself. So while we were there, we were able to observe trains traveling through at a range of speeds from 10 to about 60 miles per hour. And this is on a heavy haul line, seeing very heavy 2-mile-long grain trains, coal trains, and such. And they have been operating that tub crossing for the past 7 years. And they told us that this was little maintenance. They actually had no documented maintenance of this crossing since it was installed. So we were told to identify this one, and we went out there to make our observations and to do some instrumentation, which I'll go over soon. But notably, when we first got there, one of the things we were waiting on some trains, and we observed vehicles passing over the crossing, and we could visibly see the rail moving vertically in and out of that tub itself. So obviously the restraint system was not working properly. So we were lucky to be with a great Union Pacific crew who were able to remove the rubber stripping surrounding the rail and expose that restraint system. And it became obvious that about half to 2/3 of the clips holding the rail in place were in fact broken. So on our end, we needed to figure out why. Is that due to the train? Is that due to vehicle traffic? Is that due to some other effect? Which became evident very quick. This crossing was next to a cement plant operating very heavy trucks through the tub itself. So we were able to speak with the cement plant who said they actually had a special route where they were cleared to bring trucks through with a possible gross vehicle weight of 250,000 pounds. So in these areas, you were having these trucks pretty much impacting the rail, creating a point load and causing this damage. When you remove the stripping, you could also see the wheel paths of where the clips were broken. All the clips broken were within the wheel paths that these trucks were taking. So that became very evident that that was the issue, and it wasn't actually due to rail issues. But the Union Pacific crew we were with did end up replacing this before we did any testing on the system. So it was restored back to what they considered to be good condition. A few other issues, minor in the area. We had some drainage issues, and it caused a little bit of the pumping in the surrounding ties, but not necessarily due to the crossing itself. Here are a few pictures of those trucks crossing through. There was about 8 of those large aggregate trucks making about 8 cycles a day. So over the past 7 years, became pretty obvious that this was creating a pretty big issue for the industry. And now, especially in this, became a special case that now Union Pacific is taking a little more seriously at this location. So where I first started is what the main concern was the rail shear in these transitions. We were able to instrument the rail with a series of strain gauges in various locations, both at the transition and a location further down the track that would be unaffected by any effects of the concrete tub itself. So we were able to instrument those and collect data, and I'm going to give you some preliminary results here. What's important to note is we were subject to what train traffic was coming through the area. You're going to have all different speeds going through, like I said, from 10 to 60 miles per hour, from lighter, like mail delivery, but to very heavy grain trains. So one major approach we've taken so far in analysis, and still underway, is to kind of look at the locomotives. Those are the first vehicles going to be passing over the tub crossing. And those were going to have fairly consistent axle loading, fairly consistent total vehicle weight on those. And this could allow us to look at the speed without being concerned too much about changes in weight, changes in the car structure themselves. So this is going to be comparing locomotives coming through at different speeds. So on the left, that's a group of less than 25 miles per hour. In the middle, group of greater than 40 miles per hour. And on the right in the blue, 25 to 40 miles per hour. And that's looking at your max shear strain. And there are a few cases of in the greater than 40 miles per hour of that being having a few outliers that are of concern. But generally, the mean and median values are seeing a fairly consistent result across speed. We obviously need to take this to a few more locations. We're also going to be working on some structural modeling of these type of crossings in our future work. But we're pretty excited by our initial results, especially when the industry is looking to maybe target up to 40 miles per hour. That hopefully that might be a possibility. But obviously we have a lot more work before we make those such conclusions. On this work, I need to acknowledge the Federal Railroad Administration for their support, as well as Union Pacific. They were a huge help on site, as well as R.W. Summers, railroad contractor here in Florida.